Hey everyone, hello there. It's Friday, May 2nd, 2025. What time flies? Today, I'm digging into the archives, pulling out a real gem that's been getting some buzz. Let's see what this YouTuber was breaking down. Hey, alright. Okay, so it's paper. Let's take the title straight first. The title is RNN-T-based Losses for speech recognition on noisy targets. The title is Let's see if it would see chords tried 04.6960 feet long. It's long. Looks like arXiv 2504.06963 version 1. Why? So what's the deal with this one? It's all about teaching computers to understand speech. You know, automatic speech recognition or ASR, like the stuff in your phone or smart speaker. The big headache this paper tackles is noisy data. See, to train these task systems, you need tons of audio paired with perfect text transcription. But getting perfect transcriptions is super hard and expensive. Often, the text you get has mistakes. Words might be missing, which they call deletions. Or there might be extra words that weren't actually said insertions. Or just plain wrong words, substitutions. This is a real pain, especially for less common languages. But getting lots of clean data is basically impossible. And even for common languages, real-world data is messy. So if you just throw this messy data at a standard ASR model, especially these RNN-Transducer types, a model gets confused and doesn't learn very well. Why RNN-Transducer models specifically? Well, these models are pretty standard now and used in production a lot. They have this part called a prediction network, which tries to predict the next word based on previous words. During training, it uses the provided text transcript, but that only if that transcript has errors. It's starting from bad examples, right? And messes up the whole learning process. People try fixing similar issues for older tech called accompanying, with fancy names like start temporal classification or bypass temporal classification. These let the model be more flexible about matching audio to text. But applying those ideas directly to RNN is tricky because of that prediction network dependency I mentioned. So this paper comes along with a really neat idea. Instead of trying to clean up all the data first, which is a huge job, for changing the core ASR model architecture, they modified the loss function. Think of the loss function as the teacher grading the aide's homework. They basically changed the grading rules to be more forgiving of certain kinds of mismatches. If those mismatches look like the errors found in noisy transcripts, they proposed 3 new loss functions, all based on this RNN-Transducer framework, or starter. This one is designed to handle deletions. As missing words in the transcript, it cleverly allows the model during training to sort of skip over audio frames that don't have a corresponding word in the bad transcript, while the results are impressive. Apparently restored over 90% of the performance that was lost when using transcripts with missing words. That's huge. Second, they're bypass transducer, or bypassed. This one tackles insertions, the extra words that lets the model effectively ignore bypass tokens in the transcript. That doesn't seem to match the audio. This was apparently a bit trickier to get right, needing careful adjustment of penalties, but it still managed to recover over 60% of the lost performance. Pretty good. And third, the big one, target robust transdart, or chart. This is like the Swiss Army knife. It combines the ideas from it can handle substitutions, those wrong words, by treating them like a deletion followed by an insertion kind of. And it's designed to work even when you have a mix of all error types, which is, more realistic. For substitutions alone, it recovered over 40% of the quality loss. And when dealing with a random mix of errors, it clawed back over 70% of the performance. What's really cruel about this approach is that these new loss functions are basically drop-in replacements. You don't need to redesign the whole ASR model. You can take an existing RNN model setup. Just swap out the standard loss function for one of these, like start or chat. But it becomes much better at learning from imperfect data. That saves a lot of effort compared to massive data filtering pipelines. So, how could this be used in real life? Well, lots of ways. 1. Think of voice assistants on your phone or smart speaker. Companies train these on massive datasets, but a lot of that data is probably not perfectly transcribed. Using something like chart could make these systems more robust, understanding you better even if trained on cheaper and messy data. 2. Automatic transcription services like for meetings and lectures. These often struggle with background noise on multiple speakers, leading to errors in the initial transcript. This tech could improve accuracy by learning robustly, even from transcripts that need correction. 3. Developing ASR for languages. This is a big one for many languages. You just don't divulge pre-transcribed audio datasets. This approach lets developers use whatever noisy data they can find and still build a usable speech recognition system. That could be used for accessibility and communication. This paper scene is pretty significant. It offers a practical way to make speech recognition better, especially dealing with the messy reality of real-world data. A smart tweak to the learning rules makes a big difference. Alright, fascinating stuff from the archives today.